Okay, hello everyone. Today we're gonna go over practice quiz 2 for Dr. Wagner's OChem 2 class. Before we do the worksheet, I think it's helpful to think about, or at least look at, how heat or light will affect a electrocyclic reaction. So on the left side here, I drew this sort of image. But we're going to start with thinking about how many electrons can exist in the pi system of the electrocyclic reaction. And your answer is either 4n or 4n plus 2 electrons. And the way you count that is just you count how many pi bonds there are. So let's say I have a benzene, right? And benzene has one, two, three pi bonds. And in each pi bond, there's going to be two electrons. So that's going to equal 6 electrons total. So this would fall under our 4n plus 2 categorization. If we wanted an example for a 4n, we could draw a butene, which has it like this. And there's one, two pi bonds. And since there's two electrons in each bond, we have a total of 4 electrons. So this would be our 4n system. Then I'll keep that there and we can start looking at our reac reactants and what it means for how the the bond is going to spin in the electrocyclic reaction. So for a 4n reaction, if we induce it to heat, we're going to see conrotatory spinning. So that means that the bonds are going to spin in the same direction. If we induce the molecule to light, H nu, we're going to see disrotatory direction, which means they're going to spin in opposite directions. Opposite. And I'm saying these words, conrotatory and disrotatory, but what does this mean in actuality? So we're going to look at this molecular orbital diagram of a two two pi system, two pi systems for 4 electrons. So we could think this is our butene molecule. So since it has 4 electrons, we're going to fill up the first energy level, which is pi 1 with 2 electrons, and then pi 2 with 2 electrons in our ground state. The ground state is the most stable conformation of the pi molecular orbitals because all of the lowest energy levels are filled up and they all have, and they're completely filled as in, I mean, if you look at our excited state, you can see that we have two in the lowest and then two, and then one in pi 2 and one in pi 3. So before I get ahead of myself, let's just look at the ground state. This is the normal state that the bonds, the electrons in the bonds are going to be orientated. And so when we add heat to this ground state, it's going to cause the molecular orbitals to rotate in a certain direction. And we know from above that if we use heat, they're going to rotate conrotatory, which is the same direction. Well, why does this make sense? We should look at pi 2, which is y- our not UMO, it's actually our HOMO, the highest occupied molecular orbital. And we'll look at how these two molecular orbitals on the farthest side of the molecule, how they rotate to form a bond. And then rather than looking at butene, I think a closer image would be this, which is just a molecule rotated. These are the same. So in our second molecular orbital level, we see that we have a node down the center, which means that the molecules on either side of the nodes of that node have different phases. In order for a bond to form, we need the phases to be like to each other. So we need this positive side to be facing this positive side. So what direction is the molecular orbital going to rotate in order for a bond to form between these two? For the left side, let's say we want the light shade to bond with the other light shade. So in order to rotate that molecular orbital to make a bond, we're going to rotate it inwards or clockwise, right? And in order for this one on the right side to meet the other light shaded molecular orbital, we need to rotate also clockwise. And then this is how a molecular orbital would look after being rotated. And because these are in the same phase now, they can form a bond. And this leads to, I believe, this image. Mm, yes. I hope. Actually, no, there's gonna only be one bond there because this electron will go here and these electrons will go here, if that makes sense. Next, we're gonna see what happens after we put our diene and excite it with light. And light excites electrons to go to a higher energy level because particles of light have energy in them. And depending on the wavelength of light, it can match the energy difference from pi 2 and pi 3 for one electron to be excited. And this state is a more unstable state because, as you can see in pi 2, this is not a full molecular orbital where it has two electrons. It only has one. And this one also only has one electron. And it's kind of synonymous to a radical almost, if you want to think about why it's unstable, because there's only one electron in each molecular orbital. And there's an electron in a higher molecular orbital, which means it's higher energy. So we said when a 4n pi system gets hit with light, it's going to rotate in a disrotatory fashion. So for this, we're going to look at our SOMO, the singly occupied molecular orbital, I guess the highest singly occupied molecular orbital. And we're going to think about, well, what direction do I have to move these two orbitals in order for them to meet? So again, let's think about that. We want our light phases to meet each other again. In order for the left side to meet the right side, it's going to have to rotate inwards, which is clockwise. In order for the right side to rotate inwards, it's going to have to rotate counterclockwise, which is also inwards for the right side. And after our molecule rotates, this is how our molecular orbital is going to work. So then that's the bond. So using the molecular orbital description, we can see how for the 4n pi system, if we use heat, they're going to rotate in the conrotatory or same direction. If we use light, we're going to rotate in the disrotatory or opposite direction. And this description is the same for our 4n plus 2 pi system, except that the type of rotation is inverse. For heat, you're going to rotate disrotatory, and for light, you're going to rotate conrotatory. And the molecular orbital description is pretty much the same. So let's say that we have this molecule. Let me think if I can draw this. We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And I believe we have pi bonds there. We have at least 2 pi bonds here. No, we actually have 6. I mean, 3 pi bonds. So 6 total reactions. And we're going to imagine that the first 2 pi orbitals are filled for each side of this molecule. In the ground state, we're going to have 2 electrons in the pi 3 molecular orbital, and that's going to be our home. So we can see using the pi 3 molecular orbital that in order for our light phased molecular orbitals to meet each other, one is going to have to rotate clockwise, and the other one is going to have to rotate counterclockwise. This is how it would work after rotation. And then now these can form a bond. After we hit our molecule with light, one of the electrons gets excited. So we now look at the highest unoccupied SOMO. Highest occupied molecular orbital, which is the pi 4. And in the pi 4 configuration, the left side has to rotate clockwise. And the right side also rotates clockwise. So this is how it ends up after rotating. And now these can form a bond. So in short, for the 4n plus 2 pi system, if we're hit using heat, our molecular orbitals are going to rotate in the opposite direction or just rotatory to each other. If we're going to use light, we're going to rotate conrotatory or in the same direction relative to each other in order to form bonds for this molecule. Yeah. And if you recall, I have an asterisk above there, and it says, when opening the wing, count electrons in the pi system and in the sigma bond that will be broken. So I have this molecule on the F here, and I'm going to count how many molecules are in the pi system. So that's going to be 1, 2, 3. And the molecule that's going to be broken here. So I believe that is this one. So that means we have 3 pi bonds and then 1 sigma bond. And that means we're going to have a total of a total of 8 electrons. And since we see this triangle, that means we have thermal conditions. And if we remember from our description, if we have a 4n pi electrons and we're hit with heat, we're going to rotate in the conrotatory or same direction. Conrotatory. So then, how are we supposed to draw this molecule? To begin, we can just draw the system without any of the pi electrons, or even the sigma bond that was supposed to be there. And then since we said conrotatory, that means that these bonds are gonna rotate outward. I mean, in the same direction. So I'll just put them rotating like this. Next, we're going to imagine how our methods are going to work after we rotate our molecule. So this, the bottom method is going away from us. So that means if we rotate it inward, we are going to get, let me think. Conditions. I believe the answer is going to be, this is both counterclockwise. So if this one is going back, when we break this bond, it's going to go actually, I think we'll come back to this. It's a little early in the morning. Another tip is to be careful of sterics when rotating your bulky groups. So we see in this example below, we can rotate our molecular orbitals conrotatory in the clockwise direction. And when we rotate it in the clockwise direction and we get the product here with the CH3s on the outside of the molecule. On the bottom example, if we rotate it counterclockwise, we can see that the methyls are going to be on the inside, but then they're going to interact with each other, which is very sticky bad because methyl groups, the hydrogens are going to the hydrogens are going to repel each other because they're kind of in the way of each other. Let me see. Oh, okay. I have I have my answer for this one here. For this one, we'll think about how the the bonds are gonna move. So then we have 8 electrons under thermal conditions. That means conrotatory. The bonds are gonna spin in the same direction. In this case, I'm gonna change it to clockwise. And when these bonds breaks, the electrons have to go somewhere in order to accommodate that. So this sigma bond is broken. So the electrons are going to be donated here. If if you consider this carbon, it's going to have one, one, two, three, four, five things bonded to it because there's also a hydrogen there. So then the electrons here are going to come to this area because there's an open space for it. So this leads our pi bonds to be drawn like this. And then the question is, how are we going to draw our methyl groups? For we see that the top methyl group is pointed towards us, and we're going to rotate it clockwise, which is going away from us. So that means this methyl group is going to be facing up. This methyl group is already facing towards away from us, towards the back of the page. But since we're rotating it clockwise, it's going to come towards us, which means it'll be here in the plane of the page. And that is the final answer for that question. Let me see if I get any notes. And then I think we can start looking at the questions. And since we have all this background, I hope we can go over the questions faster. We call it the photochemical ring closure of the molecule transpires through a conrotatory process. So this is light conrotatory. And we draw the product of the thermal ring closure and describe the process as conrotatory or disrotatory. For this problem, we recognize that we're using the same molecule, but we're just changing what kind of reaction it is, photochemical or thermal. If the light reaction is conrotatory, that means that the heat reaction must be disrotatory. Disrotatory means that the bond is gonna rotate in opposite directions. So one bond can rotate counterclockwise and one bond can rotate clockwise. This means that we're just gonna draw our cyclohexene because this is a ring closing. And then we can think about where the bonds are gonna be now. In order for the ring to close, we need one pair of electrons to be donated here. Again, since let's say that the bottom pi bond donates its electrons here. This carbon here is going to have 5 things bonded to it, so it's going to push electrons over here. Again, this electron, this carbon is going to have 5 things bonded to it, so then this pushes this pi bond here. Because carbon likes to be bonded to four things. So this is how our molecule is going to work. But now we have to think about how the carbon, the methyl groups are going to work. So we have each methyl group in the plane of the page. For the top methyl group, we're rotating counterclockwise, which means that the molecule, which was once in the plane of the page, is now going to be facing towards us after we rotate it clockwise. And for the bottom methyl group, it's in the plane of the page, but now we're going to rotate it clockwise. And then after rotating clockwise, we can imagine that it's in the plane. But now, once it goes clockwise, it's going towards us. So this is also going to get a wedge bond. So then that one's complete. But now we're going to look at number B. In this year, these two people reported the activated wing opening of one to give a single isomer that goes through the thermocyclic wing closing. Right activated wing opening thermocyclic wing closing to give the molecule. Draw the single isomer of the wing closing of one in the box, turning counterclockwise. And describe the process conrotatory or disrotatory. Also describe the subsequent reaction that happens to conrotatory or disrotatory. For this problem, we see that both bonds are rotating clockwise, which means both bonds are rotating, counterclockwise. So that means both bonds are rotating in the same direction. So it's conrotatory. If the right reaction is conrotatory, that means we know that the heat reaction is disrotatory. And we know that the single isomer is a wing opening. So that means that we're just going to follow the arrow pushing mechanism here to draw what our molecule is. So again, we can start with everything besides the bond that's going to open up. And then we're going to draw everything else as normal because nothing is happening to it. I think I can draw this better. And what I mean nothing is happening to it is in my pink, there's no reaction happening on this side. So it's just going to stay as it is. So I can actually start by drawing it and then it won't be a good drawing, but it will be good for the purposes of this video. Again, we're going to skip over the the bond that once was between these two because we have a wing opening. So this bond is gone. And instead, we're going to follow the the arrow pushing mechanism that they gave us, which I highlighted in orange. The bond once connecting those two go here. The bond on the top left goes in the middle. And the bond on the bottom left now goes to the bottom right. Now, the question is, where are these methyl and hydrogen groups going to go? If my methyl is facing me now, and I rotate it counterclockwise, that means my methyl is going to be inward. So right here, CH3. And for my hydrogen, it's also rotated counterclockwise. So now that it's facing away from me, if I start rotating towards me, it's going to also be up. And the way that Dr. Wagner has it drawn in his picture is instead of having them directly facing each other, which is this is would still be a valid drawing. He has one to the side and then one to the one to the right, which is a nicer picture to draw and it gives you more space. Yeah. So that's going to B. And now we're going to look at how do you do C. When compound 1 is heated to 200 degrees C, a thermoelectrocyclic reaction, so that means we have heat, occurs to produce the intermediate that proceeds to go under a 4 plus 2 intramolecular cycle addition to give compound 2. Draw the intermediate. So it says a thermocyclic reaction to produce an intermediate that proceeds to go to a 4 plus 2 intramolecular cycle addition. I think the first thing to recognize is that we're working with heat, and then we are also working with a 4 plus 2 cycle addition, which means a Diels-Alder reaction. In a Diels-Alder reaction, we have a diene, which is electron rich, and a dienophile, which is electron poor, and they close to form a ring. So we look at our product and we see, where do I see a ring? Or more like, where do I see this? Because it's a cyclohexane with one pi bond, and we see this here in the middle of the molecule, with it being about the second wing there. So that means that our diene here must exist here. What I'm trying to say is that this in our intermediate, the diene is has this characteristic with the 2 pi bonds on this side for the diene part of the Diels-Alder reaction. So what I mean by that is I'm gonna draw my intermediate. This side, yeah, there is gonna be a diene here in order for my molecule to go over the Diels-Alder reaction that closes the ring. In this system, there are only there are one, two, three, four. There are 3 pi bonds, and then 1 sigma bond that we're gonna break for the ring opening. And I know it's gonna be a ring opening because we know that our intermediate is gonna have a diene that's open. And the diene that's open is closed in the 4 plus 2 cycle addition. So that's how I know that this fourth one is going to break open. So that means I have a total of 8 electrons. If I have 8 electrons, and I'm undergoing heat. That means that my molecular orbitals are gonna rotate in the con conrotatory direction, which is the same direction. And so what's gonna happen here is the ring is gonna open. When we start with our arrow pushing mechanism, we said that bond 4 is gonna break. So when that bond breaks, the electron is gonna be pushed up here. But now this carbon is gonna have one, two, three, four, five, like six things bonded to it. So now it's gonna push these electrons to go here. The same thing with this carbon here. There's too many things bonded to it. So this electron is good. Those electrons are gonna be pushed here. Again, this this bottom carbon is gonna have too many things bonded to it. So it's gonna push its electrons here, where there is space to accommodate the additional electrons, called the pi bond. So then after our arrow pushing mechanism, we can draw our pi system like this. And we've drawn the pi system, but we're still missing the rest of our molecule. And again, the same idea holds. There's no reaction going to happen on this side. So this means that it's it's just gonna be the same before and after. So I'm just gonna draw it the same way. And if you wanted to, we could think about the conrotatory, disrotatory again. Let me draw this first. So we said that this reaction is conrotatory. So then, in order for the sigma bond to break, these are gonna rotate in the same direction. And I'm gonna pick clockwise. If this bond rotates clockwise, what how how is our big thing that didn't get reacted going to work? It was once in the plane of the page, but now it's rotating sort of, oh, it's rotating away from us. So that means, wait, yeah, it's rotating away from us. Actually, I don't think I can make that. I don't think I can make that description because if we think about it here, this is a sp2 carbon, and sp2 characteristic is drawn like trigonal planar. So even if I even if I rotate the molecule, the bond, it's gonna stay in the plane. I believe it would stay in the plane of the page. So we wouldn't have to worry about if it was, oh, it's if it's going towards us or if it's going away from us. That's that's what I'm thinking. Because if you look here, I'm going back to the first one. Let me use a new color. this bond here, this is a CsP3. That means it's gonna be, let me look that up. Confirm, confirmation. It's gonna be sort of, I believe the word is tetrahedral. Yes, it is tetrahedral. So one's gonna go on top, but then one's gonna go this way, one's gonna go this way. This one's gonna go to the back. So in a way, this is the wedge bond. This is the dash bond. And these two are just in a plane. So that's why in this example we were worried about if it was wedge or dash because it's a sp3 carbon. And this one, it's just a sp2 carbon, which means that the mercury orbitals are all in a plane. So we didn't have to worry about like if it was going away or towards us when it was rotating. Sorry, gang. Anyways, we are gonna think about is could our intermediate go through a Diels auto reaction? And as I said before, we just need a diene, which we have here. Diene, check. And we need a dienophile. And I actually have a dienophile already in the molecule, which is this lone alkene. So check. So that means this is the correct answer for our description because we opened the wing through the thermal electrocyclic reaction and we've drawn an intermediate that can undergo a 4+2 cycle addition or a Diels auto reaction to give compound 2. And if you wanted to see the arrow pushing mechanism to get to our final product, what would happen is, see, the top pi bond would go here. This pi bond would attack this carbon here. And this pi bond would attack the top carbon here. And this would result in our product. Yes. So then now we can go to the second page. In a recent, sorry, in a recent paper, a Friedel-Crafts alkylation mechanism was proposed for coupling diazo esters to a variety of aromatic compounds. Write a mechanism of reaction catalyzed by citric acid with benzene to give methyl 2,2-diphenyl acetate 2. Okay, the first thing is what is a Friedel-Crafts alkylation? I have it here. A Friedel-Crafts alkylation is a type of electrophilic aromatic substitution. What is a electrophilic aromatic substitution? EAS. This reaction adds a substituent to benzene and other aromatic compounds. This is a two-step mechanism where the first is electrophilic attack. That means we need an electrophile, some sort of electron deficient molecule. The second step is proton loss and aromatization, which is just regaining the pi bonds so that it is prana conjugated, and four, I believe 4 and +2 electrons. Give me the characteristics to be aromatic. Yes, you need 4n+2 electrons, cyclic prana conjugated. Beautiful. Requires an reactive electrophile to reach the high energy transition state or intermediate, and this means the aromatic ring is the nucleophile. And I took this from the lecture, so you can just look at it. But we're gonna see this sort of mechanism appear once I draw my reaction here. And the second thing to recognize is that HOTF is tryptic acid. And tryptic acid is a strong acid, which means it donates hydrogen atoms. And this is the structure of tryptic acid. This is going to be important because we're going to steal this hydrogen from the molecule and then we're going to give it back later because it's a catalyst. And that's what catalyst means. It speeds up the reaction, but it also is consumed in the reaction but gets regenerated later. Okay, first things first. We're gonna recognize that this this is how a molecule works in another reality. This sort of corresponds to being able to draw these resonance forms for molecules, Lewis structures. We know that nitrogen is more electronegative than carbon. And this means that there's like, even though this is a net positive, a positive form of charge, the electrons are still going, this nitrogen is still stealing electrons from the carbon that exists here. So has a somewhat partial positive charge. This means that this is our electrophile. That means our benzene is the nucleophile and it's going to attack this electrophile at that carbon. And let me restate that a Friedel-Crafts alkylation forms a CsP3 and a CsP2 bond. So we have our nucleophile here, our benzene, and it has 6 pi electrons. Any one of those pi bonds can decide, oh, I'm gonna attack this carbon here because this pi bond has 2 electrons and it's the nucleophile, so it wants to give these electrons off. It has the ability, because of these pi bonds, to donate one pair of its pi bonds to another molecule to form a bond. But we see that when we push this electron here, push this electron to the carbon, this carbon is going to have 1, 2, 3, 4, 5 bonds. And that's more bonds than carbon wants. So carbon in turn is going to push electrons from the double bond with nitrogen up to the nitrogen, which in case we've said before, nitrogen is more electronegative than carbon. So it would accept the electrons being given to it. Next, we have, so then we're going to just draw the next step after this attack. So we have Also, don't forget to draw bond segment pi bonds on the electrophile in the benzene axis. So this is how our molecule looks now. And then one more. It has we'll take this. Now, where this carbon, when this ben when this benzene attacked the electrophile, it lost the pi bond, right? So that means that there's going to be a positive charge on the nucleophile region where the only has three things bonded to it. You can see here, there's going to be an H here. There's going to be H here. But then this carbon only has three things bonded to it, so it's a net positive charge. And what's going to happen next is that N2 nitrogen gas is a good even group. So how is it going to leave? It's going to leave because the top nitrogen, sorry, is going to donate its electrons to the double bond. And we know that nitrogen wants five things bonded to it. And this nitrogen here has 1, 2, 3, 4, 5, 6 things attached to it, but it only wants five. So for it to get five and get rid of its negative form of charge, it can donate two electrons to its bond with the other nitrogen, which means that this bottom nitrogen is going to have 1, 2, 3, 4, 5, 6 things attached to it, which also makes it negative. In order for it to leave the molecule, it's going to take the electrons that are in the bond between the nitrogen and carbon and just give it all to the carbon. And this allows the N2 to leave as nitrogen gas, leaving this as what we have right now. Let me draw this is how it's gonna look. And because both machines, five things bonded to it, is gonna has five things bonded to it, so there's no more formal charges attached to the nitrogens. But as we see on our molecule on the bottom with the two wings, it's actually gonna have a negative charge because the nitrogen pushed the electrons onto this carbon, right? So now this particular carbon has 1, 2, 3, 4, 5 things attached to it, which is a negative formal charge. Now this is when our acid comes in, because we know that acids donate hydrogens or accept electron pairs. So I'm going to draw our acid here the way that he did. And what can happen is me draw this another to signify that there's a bond here. Is that these electrons are gonna attract this H, and the bond between the H and the O is gonna dissipate as it pushes the electrons to the O. Next, we're gonna have this. I keep forgetting to draw bonds in that. So don't forget to draw bonds on your wings where there needs to be bonds. So this is this is what we have right now. I'm gonna draw H here, OTF. Now, if we think about it, this OTF has the oxygen with 6 things bonded, or with 7 things attached to it. And we know that oxygen normally wants only 6 things attached to it. So this gives it a formal negative charge. Well, if we think about it, this negative charge exists here, and this positive charge exists here. What can we do to make all of these molecules happen? Well, let's see what we're missing comparing what our intermediate here to our final product. Well, it appears that our final product has 3 pi bonds in the molecule, but our intermediate right now only has 2. So this should give us the hint that, oh, we should make a pi bond. How can we make a pi bond? We can steal a hydrogen and form a bond from there. Since there are already pi bonds on the bottom, we shouldn't try to steal a hydrogen from there because that would mess up the bonding that's already there. Well, what other carbon doesn't have a pi bond? It's the one directly attached to the rest of the molecule. So our goal is we are going to take the hydrogen that I've drawn in yellow, and OTF has the means to take that hydrogen because it has enough electrons to do so. So it's just going to come over, take that hydrogen. The bonds between the carbon and the hydrogen are going to push into the ring and the pi bond that we need. Okay, so then this is what's happening now. This should be our final answer. CO2 H. Yeah. And you don't have to draw this. You don't have to draw the hydrogen on top. And these two are the same. So we did it. And we generated our catalyst as well. So that's how we know that the reaction worked out too, because our catalyst was consumed in one step and then reproduced in another step. Okay, now it's time for the last question. This one, I looked at it, I was able to answer 2, but don't worry, we got this. Cis rose oxide is a fragrance. Only the cis isomer gives rise to the floral fragrance. Both cis and trans rose oxides can be produced in roughly equal amounts by treating the diol the product of the sodium sulfate reduction of the allele. Yes, 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 yes. Okay, the last one is what's important. Show a detailed air pushing mechanism for converting the diol to rose oxide. Dr. Wagner kind of gives you a lot of information to sort of confuse you, but all we have to do is show the air pushing mechanism for the diol, which is this one, to the rose oxide, which is these. And he has this reaction here, right? But you can also kind of just ignore it because I don't think we learned how to do this. And even if we did learn how to do it, we don't have to show the air pushing mechanism for it. We only have to show this one. So we can start by recognizing what reagents we're using. We're using H2SO4, which is sulfuric acid. And remember, what do acids do? Acids donate hydrogens. They yeah, use acid. They accept electron pairs. This is going to be helpful for us because we can recognize that we have okay, we can look at what are the differences between this molecule and this molecule, the reactant and the product. Well, we see that there's no H here. There's an alcohol here, but there's no alcohol in the product. You can also see that there's an H here, but there's no H here. In place is just a bond. You can also see that the pi bond was moved down. So the first thing that's gonna happen is that we're gonna recognize that let me draw this first. Um, that sulfuric acid, strong acid donates H plus. So these alcohols can actually steal electrons. I'm not sure electrons steals a hydrogen from this acid, and this leads to this happening. Um, and you could also argue that it's gonna take the electron attached to the pot. That kind of looks like the alcohol could also take hydrogen. Wait, what I'm saying is that you could say that this alcohol also takes an acid from, takes hydrogen from the acid, but wait, I'm looking up. Okay, what I'm gonna say is that you could recognize that the sulfuric acid could react with the alcohol inside the ring type structure. But we also recognize that our final product has an oxygen there. When we when the alcohol takes the hydrogen from sulfuric acid, we create a water group. And we should know that water is a good leaving group. which means that it's gonna take electrons from the bond between the C and the O plus HSO4. So this is let me draw this in a different color. Water is gonna use. So I have a OH, and then we're gonna have a positive charge here because the carbon there only has three things bonded to it. But now, but now, yeah, that carbon only has three things bonded to it. And carbons usually want four things bonded to it. So it has one S than what it wants. So it has a formal positive charge. Okay, the next step is thinking, how can I make this positive charge? How can I move this? How can I manipulate this molecule such that the positive charge is gone and it looks more like my product that I want to make? Well, we said it before. We said that there was a pi bond here, but it seems the pi bond has moved down. So that means that the electrons from the pi bond have moved down to change where to change where it is to make us closer to our product. And another thing you can think about is, let me draw it first. This is kind of like, this does not look good. This is kind of like, I believe, a 1,2 hydride shift. Because let's recall the stability of alkenes. A more substituted alkene is more stable. In the top depiction, this is how our alkene looks. In the bottom depiction, this is how our alkene looks. Which one is more stable? The bottom one is more stable because it has three subs, which is the three R groups, and the top one only has two subs. So this one is more stable. So our molecule is going to spontaneously undergo 1,2 hydride shift to make a more stable alkene. And let me see something. Okay, we recognize that this isn't, I don't think this won't be tested, but if we think back to the last practice quiz, the more stable alkene is the thermodynamic product. Yes. So now we can think. When we move that pi bond, we took away the electron density from this guy. And this guy has hydrogen that's not absorbed, that's not um drawn explicitly, but it exists. So this carbon only has three things bonded to it. You know, carbons want four things bonded to it. So three, one, yes, and four is three. So this has a positive charge. And then we ask the question again. How can I make my molecule look more like the end molecule? Hmm. I see that my H is gone. Give me that thing. My H is gone, and there's now a bond between a new carbon oxygen bond there. How can that happen? Well, let's think about it again. We have we had sulfuric acid, right? Sulfuric acid, after it uses one hydrogen, becomes a hydrogen sulfate with a negative charge. Hmm. Once a strong acid becomes uses a hydrogen, it becomes a weak base. A weak base. What do bases do? Bases, time. Bases take hydrogens slash donate electron density. Okay. So then we can think about how this molecule looks right now after took an electron from it. O H O 1, 2, 3, 4, 5, 6 with a net negative charge. Hmm, what can we do? We can see that this base wants to take hydrogens. Is it going to take hydrogens from the OH, or is it going to take hydrogens from the own H here? Well, it's going to take the hydrogen here because if it took it from the other place, it would have that carbon would have a net 2+ formal charge, which is really the carbon really doesn't want to be in that state. But because oxygen is more electronegative than carbon, or even than hydrogen, if it's okay with having a little more electrons and accepting a formal negative charge. So when we take that hydrogen here, it's going to push electrons. Let me redraw this so it's more clear. This oxygen going to take that hydrogen. The OH bond is going to dissolve, and the oxygen is going to take the electrons because it's more electronegative. Next, then what happens next is, let me draw it. Positive, oh, 2, 3, 4, 5, 6. Oxygen now has 1, 2, 3, 4, 5, 6, 7 things bonded to it. And we know oxygen normally wants only 6 things bonded or attached to it. 7 is one more than 6, so then it has a 4 more negative charge. Hmm. And this actually regenerates our patterns. Okay, so our last step. What is we have an oxygen with a negative charge and a carbon with a positive charge. Hmm, I think a positive and a negative charge attract, and I think they're gonna form a bond. And I think it would form the final bond that we need to form our cis or trans rose oxide. So the mechanism that happens here is the oxygen is going to donate electrons to the carbon and it's going to form the bond. And as we've, I don't, as we've, this is going to take us back to OCHEM 1, but if you recall, when there is a wing closing, the the oxygen can actually attack from the front face or the back face of the molecule. So this really means dash, I mean wedge or dash bond. And that's because if oxygen attacks from the back of the molecule, right? Where is where's this whole thing gonna go? Is it gonna go from the back or is it gonna go from the front? Oh, well, this is kind of like uh intramolecular SN2 reaction, right? So then, so if oxygen is going to attack from the back, it's going to force this whole thing to start facing the front. And that is how we get our attack, attack from back. That's how we get our cis conformation. If the oxygen attacked from the front, that's how we get our trans conformation. Because, like, think of it this way. If some guy, some person just comes around and pushes you from the back, are you gonna move back or are you gonna move forward? Well, you're gonna move forward. So the bond that's here is gonna move forward when the oxygen attacks the carbon from the back. If someone pushes you from the front, the bond there is gonna move to the back. And so that's why we have these dash and wedge bonds. Then for my final note, I'm just going to say it's an SN2 like dosing. And I don't have, I'll say I don't really have SN2. And then I'll write intramolecular. And then I don't want to talk too much, but if you wanted to understand that more, I'd suggest looking this up and seeing if it's real. But that's how I would answer the quiz 2. And I think the classes that the quiz covers is class 4 to class 7 in it. So I would advise people to also study photocrafts oscillation in addition to the other kinds of freedom crafts outpatient. I don't think class 8 will be on it, so just study class 4 through 7. And that's all. I hope this was helpful and good luck on the quiz, everyone.